Analog to digital converter. Figure 2.6 shows the basic components of an ADC. Sampling. Converting the continuous time XAT, which has a limited frequency band, to a discrete time signal with continuous amplitude denoted by Xn, by sampling the continuous time signal at the sampling instance. Quantization. Converting a discrete time signal with continuous amplitude to a discrete time signal with discrete amplitude denoted as xq of n. At this stage, it can be called a digital signal. The value of each signal sample is represented by a selected value from a limited set of possible values. The difference between the quantized signal and unquantized one is called quantization error or quantization noise. Coding. The quantized samples of the signal are represented by a sequence of B bits. Dynamic range. Dynamic range for an ADC is defined as the ratio of the maximum allowed levels to the minimum detectable signal and is expressed in decibels as dynamic range, or DR, is equal to 20 times log 10 of 2 to the power of B. B represents the number of bits in ADC. Okay. Quantization noise. It is a noise-like error or distortion that occurs due to rounding or truncating the analog signal, to the closest quantized value. For an ADC with B bits, the number of quantization levels is equal to 2 to the power of B, and the distance between the levels, that is the quantization step size, Q, is determined by the following equation. Q is equal to V full scale over 2 to the power of B minus 1, or an approximation you see, where V full scale is the full scale range of the ADC with bipolar signal amplitude. Okay. The maximum quantization error for the case where the values have been rounded up or down is equal to plus minus Q over 2, or half Q. On the other hand, it's assumed that the quantization error for each sample, which we represent by E or error, is random and uniformly distributed in the distance plus minus half a Q, and with zero mean. As a result, its probability density will be P of error is equal to 1 over Q. Meanwhile, the quantization power or error variance is equal to sigma e to the power of 2, leading to Q to the power of 2 over 12. Okay? This is the error variance. For a sinusoidal input, the ratio of the maximum signal level in the passband to the signal level in the stopband, denoted as minimum attenuation or A mean, will be equal to maximum passband signal level over stopband signal level is equal to Vmax over square root of 2 over sigma e, or standard deviation of noise, which leads to square root of 1.5 times 2 to the power of B. This is the minimum attenuation denoted by A mean. It can be expressed in decibels. A mean is equal to square root of 1.5 times 2 to the power of B, which in dB leads to 6 times B. Please consider the difference between A min and V max or A max. A max is maximum amplitude in a sinusoidal signal, or Vmax, but A min is minimum attenuation. So A here is for attenuation and V or A here is for amplitude. Okay. Suppose a Butterworth filter with the following characteristics is to be used. We have got familiar with it in earlier lecture. At the frequency Fs, or a stopband frequency, which represents a stopband, we have minimum attenuation is equal to square root of 1 plus Fs over Fc, all to the power of 2 times n. N is the degree of the filter, which is equivalent to square root of 1.5 times 2 to the power of b. Please consider that here the term is in denominator and here it's free term because attenuation is a negative number. If Fs is considered to be equal to greater than 2 times sampling Fs or stopband frequency, the acceptable limits for the sampling frequency is obtained. On the other hand, the aliasing frequency in this case is equal to Fa is equal to Fs minus Fc. So two important equations. Fs is greater than 2 times Fs and Fa aliasing frequency is equal to Fs minus cutoff frequency. Anyhow, the aliasing level at cutoff frequency will be equal to, without any pronunciation of the, just reading, you may read the equation, very simple one. This level should be smaller than the level of quantization noise. For a sinusoidal input, the average power of the signal is equal to half of A max to the power of 2. The ratio of the signal power to the quantized noise power, that is SQNR, signal to quantized noise ratio in dB decibels, is equal to 10 times log 10 of A max to the power of 2 divided by 2 over Q to the power of 2 divided by 12, which leads to 6 times B plus 1.76 dB. Okay? Now, proposition number 2.3. Anti-aliasing filter or filtering considering the number of ADC bits, a very important design. If B of ADC is equal to 16, meaning that 16 bits are used, and we use a 4th degree Butterworth low-pass filter, and the cutoff frequency of the signal is equal to 4 kHz in normal speech, okay? Find the minimum attenuation in the stop band of the anti-aliasing filter. 2. Find minimum Fs. 3. Find the aliasing level and its ratio compared to the signal level at cutoff frequency for the above values. Now the solution. Okay. Minimum attenuation. The same equation we got familiar. Here it will be A will be 8026.8799 and dB minimum attenuation will be about 98 dB, right? What about minimum sampling rate? Here again we rewrite the equations we got familiar with it. Just consider Fs here instead of normal f, because we are trying to find a stop band frequency. So fs will be roughly about 67.3 kHz, and fs will be twice that number, meaning that 135 kHz. Okay. In order to have the recording length shorter, we have to have somehow hurry. Aliasing level. FA will be Fs minus Fc, leading to 131 kHz. What about the aliasing level in this case? It will be really negligible, so don't worry about aliasing level. It won't have any harm. Right. Take home 2.2. Analyze the role of increasing or decreasing the number of ADC bits in determining the sampling frequency per fixed degree of the anti-aliasing filter. Okay? Do all cases available for you. 2. Analyze the role of increasing or decreasing the degree of anti-aliasing filter over Fs while the number of ADC is kept constant. Now, the last part in the system, DAC, digital to analog converter. Here you see in the figure, zero order hold DAC, original signal, and stepwise signal, staircase approximation. Okay? The process of converting a digital signal to analog is done by connecting points in the digital signal together using interpolation whose accuracy depends on the quality of the DAC. The above figure illustrates a zero-order Hall DAC. The operation of maintaining zero-order hold is the same as step-quant approximation. The sampled signal spectrum contains the repetition of the spectrum of original signal in multiples of the sampling frequency. Right. By passing this signal through an ideal low-pass filter with the same bandwidth as the original signal, we can extract only the spectrum of the original signal and thus reconstruct the original signal, which is continuous. However, a typical DAC converts the output signal to a stepped waveform instead of the theoretical impulse train. The effect of zero-order hold is as if the signal had been passed through a filter whose impulse response is a pulse with the width of the sampling interval. Okay. The domain response of such a filter has a form of sink, which should be considered. In the time domain, we have the convolution of a pulse with the processor's output signal. In the frequency domain, the frequency response of the processor output is multiplied by an effect of sink, which acts like a low-pass filter and strongly weakens the high frequencies, resulting in a distortion in the DAC output. This effect can be compensated by adding an inverse filter in the form of the domain response of x over sine of x. In the DSP processor, or a reconstruction filter which is called equalization. The issues related to DAC design are quite similar to those mentioned for ADC. Reminder of some essential formulas. We will keep them for you to study later. This equation is very important. Please write it down for future usage. And this one is important as well. And here you see another important equation. Okay, we will later use them frequently. And analog Fourier transform, here you see very important relations. If we have a delta t in time domain, what will be the Fourier transform? Here you see, this is very important. Of course, I know you are familiar with it. A shift in delta, what will be the result here? Okay, impulse train and having impulse train in another domain. And what about sinus or cosine? Here you see the relations. And okay, that's the end of this part.